You know, for over a century, physics has been haunted by this deep riddle. We all know gravity as this incredibly complex geometric thing. But what if it wasn't? What if, at its heart, it could be described by something way, way simpler? So today, we're going to dive into the mystery of scalar gravity, a real graveyard of failed theories, and the one huge conceptual leap that might have finally solved an impossible problem. And that is the question, right? That's the heart of our story. Could gravity, the force that literally bends light and warps the fabric of space-time itself, really be boiled down to just a single value, a scalar at every single location? It's such an appealing idea, this quest for the ultimate simplicity. But for decades, the answer from both theory and experiment was a big, fat no. So why is this so tough? Well, take a look. On the left, you've got a scalar field. It's kind of like a weather map that just shows the temperature. Each point has just one number. Super simple. But on the right is what we know works. Einstein's gravity, a tensor field. That's more like trying to describe the stress and strain inside a chunk of metal. It's got multiple values, multiple directions, all happening at every point. The real challenge, the impossible part, was trying to get all that complexity on the right to somehow pop out of the simplicity on the left. Okay, so to really get the breakthrough, you gotta understand the breakdown first. Let's take a look at why every single attempt to build a simple scalar theory of gravity was pretty much doomed from the get-go. So the first big swing at this came from Gunnar Nordstrom, and this was even before Einstein had finalized general relativity. His theory was beautiful, it was elegant, and it basically proposed that gravity was quite literally nothing more than a scalar field. The core idea, the big assumption, was that the scalar is the gravitational force. A really bold idea, but it ran smack into a brick wall of reality. And boy, were the failures clear. Nordstrom's theory predicted that gravity wouldn't bend light at all, which, as we know, is totally wrong. It also had zero room for gravitational waves, because a simple scalar just can't describe those shearing, stretching transverse waves we've actually detected. Now, later theories like Brand-Sticky were a bit smarter. They kept Einstein's tensor and just added a scalar to kind of modify it. But that was just slapping a Band-Aid on it, you know? It wasn't a real solution because you still had to assume tensor gravity existed from the start. You couldn't derive it. And this is the real culprit. This is what put the nail in the coffin. The no-go theorem. It's basically a mathematical proof that says, nope, you can't do that. You just can't build a complex machine out of a single simple part. A scalar field has 1 degree of freedom, but a gravitational tensor field needs 2. The numbers just don't add up. The math flat out forbids it. This was, for all intents and purposes, a dead end. Game over. All right, so if you hit a mathematical wall like that, a fundamental no, what do? You can't turn a scalar into a tensor. So you change the entire question. And this is where the big paradigm shift happens. A complete rethink of what the scalar field is even supposed to be doing in the first place. And this is it. This is the absolute game changer. This insight comes from a new framework called dynamic vacuum field theory, or DVFT. It says, hey, everybody was making the same basic mistake. They all assumed the scalar field was gravity. But this new idea is totally different. It says the scalar field isn't the force itself. It's a description of the medium the force travels through, the vacuum. Gravity is what the vacuum does in response. I mean, the shift in thinking here is just massive. On the one hand, you have this fatal assumption that doomed 100 years of theories, scalar equals gravity. But the new idea, on the right, is what unlocks the whole puzzle. The scalar describes a medium, and gravity is that medium's reaction. By putting that little separation in there, you suddenly create a path for all that beautiful complexity to emerge from something simple. Okay, so how does this actually work? How do you get gravity from stiffness? Well, it all starts by treating the vacuum not as just empty space, but as a physical material, something with properties you can actually describe. All right, so in this DVFT model, the scalar field gets a little more detail. It's described by 2 numbers now. The first one, rho, you can think of it like the stiffness of the vacuum, kind of like how taut a rubber sheet is. The second one, theta, describes its coherence, or how orderly and in sync it is. But here's the absolute crucial part. These numbers aren't describing gravity or space-time directly. They're describing the internal state of the vacuum itself, the fabric of space-time. And this next analogy, this is where it all clicks into place. In high-energy places, like right near a star, the vacuum is in what's called a stiff regime. It acts like a super tight drum skin. Now, if you try to just push down on it, that's a compressional, scalar-like disturbance. It barely moves, it resists. But if you tap it, it sends out these sharp transverse shear waves across its surface. And then way out in the deep field, where there's low energy, it's more like a soft foam. It can be compressed and just behaves totally differently.
Okay, so let's bring this all back. How does this whole stiff vacuum idea actually solve the original puzzle? How does it produce the complex tensor gravity of Einstein that we know and observe?
And boom, here's the payoff. Where Nordstrom had no tensor waves at all, DVFT has them emerge naturally from the vacuum's own response. Where Nordstrom got light bending completely wrong, DVFT gets it right, specifically in that stiff regime. The conceptual advance is everything. We've gone from this simple, wrong idea of scalar equals gravity to this incredible new concept. A scalar defines a vacuum state, which then produces a geometric gravitational response. So let's just walk through the logic, step by step. First, our scalar field sets the stiffness of the vacuum. Step 2, that stiffness then acts like a filter. It pretty much kills any of the wrong kinds of disturbances and only allows these shear type waves to travel through. Step 3, what are shear distortions of spacetime? They are, by definition, the spin-to tensor waves of gravity we observe. So, step 4, and this is the magic, tensor gravity isn't assumed, it isn't put in by hand. It's selected by the physics of the vacuum itself. And this, to me, is the most clever part of the whole thing. The theory doesn't break that old no-go theorem, it just sidesteps it. The theorem says you can't turn a scalar field into a tensor field. And DVFT is like, yeah, we know, we're not trying to. Instead, it uses the scalar to set the rules for a medium, and it's the medium's collective behavior, its response, that is a tensor. The theorem was right all along. It was just being applied to the wrong problem. Okay, so let's zoom out. What does all of this really mean? Because this isn't just some clever mathematical trick. It really represents a fundamental shift in how we think about the fabric of reality itself. You know, for 100 years, we've basically pictured spacetime as just the stage, the passive backdrop for the play of the universe. DVFT suggests that spacetime is one of the actors. It's an active, physical medium that can be stiff or soft, coherent or messy. This moves us away from just pure geometry and into a physics that looks more like materials science, which could, potentially, be a bridge to a quantum understanding of the vacuum. And all this leaves us with one final kind of mind-bending question. For the longest time, we've looked out at the cosmos and seen, well, emptiness between the stars. But maybe we've been looking at it all wrong. Maybe what we call empty space is actually a complex, dynamic material, and the force we call gravity is simply the story that material is telling us.